And now, it's a pleasure to start the morning with the talk of Alice Guionnet. She will talk about some results related to random matrices, so heavy-tailed matrices, topology, and non-commutative entropy. And she comes from Lyon.
Okay, thank you very much for the introduction. And thank you very much for the invitation. So when Nalini invited me to give this talk, for some reason I just thought I should talk about this work that we completed with Charles, Bordenave, and Camille Male about 1 year ago, at this end of 2024. And so it's basically about random matrices with heavy tail. So I will define all this, and large deviations, so entropy. And also the relation with random graphs. So I thought there were kind of geometry and underlying all that, these big objects which are random matrices. Okay, so to start slowly, so I will consider a matrix, so nothing crazy about it. It's a n by n matrix. It will be self-adjoint. The entries will be real or complex. I mean, it's in most of the results I will tell you it doesn't matter. So, and the kind of question that I will ask is what is the typical distribution of the eigenvalues of this random matrix? Or if I look at more sophisticated object, what is the joint distribution of several matrices in the sense of free probability, or the traffic distribution introduced by Male, that I will show you what it is. And also what is the probability of deviation, so what is the probability that it doesn't take this typical behavior. And what I want to discuss is the difference when you have what we call light tail, which is a well-known universality class of Gaussian matrices when the entries are Gaussian, compared to what happens when you don't have finite moments, for instance, or when you have entries, so basically entries which can be big. So somehow light tails, you have to think about matrices with lots of small entries, whereas, as we will see, heavy tail are basically entries where you have finitely many entries which are not zero or not very small, and these entries are of order 1. So it really is a very different kind of universality class. So let me explain that on the example of one matrix. And so there is this very well-known theorem by Wigner, which is kind of the meta-theorem in random matrix theory, which says, so if you take here the entries of your matrix to be of the form yij divided by square root of n, and the distribution of the yij will not depend on n. Okay? And you assume that your entries are centered, and the variance is 1. Okay? So this could be complex or real. You look at the eigenvalues of this matrix xn, and the empirical measure of the eigenvalues is this measure on the real line, which puts a mass at every eigenvalue. Okay? And so the Wigner theorem tells you that this empirical measure, it converges almost surely towards the semicircle law. So what does it mean? It means that for every bounded continuous function on the real line, if I evaluate my empirical measure on this bounded continuous function, it will converge to the integral of f under the semicircle law, which is just the square root of 4 minus x squared dx over pi. Okay, so it's a semicircle law with radius 2. Okay, so I'm sure that I imagine that Raman will tell you much more about that and more. And I would like to show you one proof of this to compare with what will happen in the case where you have a heavy tail. And I take, there are many proofs of these results. And I will discuss the one which is based on the convergence of the Stiglitz transform. Okay, so you take some z which is complex, not real. So you can define the resolvent. And you take the trace and you divide by n. Okay, so it's also the integral of the empirical measure against this function 1 over z minus x. Okay, so it's enough to show the convergence of this object for all z which are not real, or even all z which are in some set with accumulation point, because this function being analytic, if you show its convergence on a big enough set, you show it everywhere in the domain of analyticity. And if you want to, so this will allow to show you the convergence of the empirical measure when you test it again, function which go to 0 at infinity. Okay, so this is vague convergence, and then you have to work a bit more to show that somehow you have nothing bad happen at infinity. Okay, and so one way to get this convergence is by getting some equations for this Stiglitz transform. And one way to get such an equation is to use this Schur complement formula. So Schur complement formula is a formula from linear algebra, which tells you that if you take the resolvent and you take the entry II, you can write it as 1 over, so z minus xii, the entry over the diagonal, minus the scalar product. So what is that? It's the resolvent of the principal minor. So, okay, so it's a n minus 1 times n minus 1 matrix, which you extract from Xn by just erasing the i's column on the row. So you take the resolvent and you take the scalar product with the vector xi, which is the vector where you have just the entries coming from I. Okay, so why can this be helpful? So the idea is that this term can eventually be given in terms of this Stiglitz transform. Okay, so why is that? So, well, you can just expand that. Okay, so that's just a definition. And then you can see that the term where j is different from k are going to be neglectable. And you can just take here the L2 norm of this guy, and you see it's the L2 norm is of order 1 over n. So at least in probability it goes to 0, but if you use more sophisticated tools, you can see it goes to 0 in much stronger sense. So then you are left with this term. And here you see that somehow what is good is that this principal minor, it's independent of the x squared gi, okay, because of the definition of the matrix I'm considering, they have independent variables above the diagonal. And therefore, you can use eventually law of large number. Okay, so here you have IID variables which are integrable. And so conditionally to the entries in this minor, you can use the law of large numbers. So this means replacing xij squared by its expectation. Okay, and when you do that, so what you realize is that this term is approximately, so 1 over n, the trace of this resolvent of the minor. The minor is very close to the original matrix. It's a rank 1 perturbation of your original matrix, so you find that it is approximately the Stiglitz transform. Okay, so like this, you see in one slide, you can prove Wigner's theorem somehow, because this, when you sum this up, and you use this approximation of this term by Gn, you find that because the entries on the diagonal of order 1 over square root of n, you find that the Stiglitz transform satisfies this equation. So it's a quadratic equation, and you have two solutions, and you can find which one is a good one by just looking at what happened at infinity. Okay, it has to go to like 1 over z. Okay, so this, and what you find is that this solution is the Stiglitz transform of the semicircle law. Okay, so this shows that Wigner's theorem holds when you take function.
Do you use only two rulers?
Yes. I mean, here for the law of large number, you really need just the inner one. Okay, so that's the proof, but you see that crucially here we use that we can use the law of large number, and what will happen with Evitel is that actually the law of large number does not hold, and so we will get a different result. And so this is what is going to happen. So what will I assume about the entries now? So there will be Evitel, and I assume that if I take the Fourier transform of the square of the entries, minus 1, and I multiply by n, it will converge towards some function. Okay, and here to simplify, I will assume that this function has this type of form. I mean, it will be helpful in the proof, but it's kind of technical. Yeah. Okay, and then so maybe I should say that the example that we have in mind follows this kind of hypothesis. So what is the example we have in mind? So if we take your matrix to have only 0 or 1 entries with a Bernoulli distribution, so it's the adjacency matrix of the Erdős-Rényi graph, then you can see that so this will be 1 with probability p over n. So what you will get is just p times exponential it minus 1 at the limit. Okay. So, and if now you take the Hadamard product, which means that the entries will be the product of a Bernoulli variable times some random variable which does not depend on n, then you can also do this computation. So, I mean, I think it's so I'm just saying that this will be ij, so it will be aij squared minus 1. So, expectation. So this will be so 0 if b is equal to 0. It will be p over n times the expectation it aij squared minus 1. Okay, in this Hadamard product case. Okay, so you see that this type of hypothesis is then verified with this function phi. And so the other type of matrices that people have considered quite a lot is Levy matrices. So in this case, the entries are alpha stable. So this means that somehow the tail at infinity decreases at t minus alpha with alpha which is smaller than 2. Okay, so you don't have a second moment. And then you have to renormalize your entry by n1 over alpha. And you can see that you will have again this type of property with this type of function. Okay, and the relation actually with the two is that if you do you see the slides when the light is open? Yeah, so maybe you can keep the light open. So. And what I just wanted to say that the probability that your entry, so yij over n1 over alpha, is greater than t. So this will be, by definition, like 1 over n to the t alpha. Okay, so you see that somehow entries which are of order 1 have a probability to appear with a probability of order 1 over n. So exactly like the B. Okay, so it's also a sparse matrix in the sense that most entries will be very small, and they will be of order 1 with probability of order 1 over t alpha over n. Okay, so it's kind of the same, but you see here that you can take t as small as you wish. Okay, but it's the same type of matrix where you have very few entries which are non-zero and a few which are very big. Okay, so in this, maybe also a remark is that the Wigner matrix actually also satisfies this, because if you have a light tail, because then xij square will be, so if you look at exponential it yij square divided by n, so this will be minus 1, this will be like it yij square over n, so the expectation will be like it divided by n. Okay, so also actually this definition also holds for light tail matrices, but of course light tail matrices are not of this kind. So actually this theorem includes the case of Wigner theorem. Okay, and so what we show is that also in this case you have convergence of the empirical measure, but now the limit will depend on this function phi in general. Okay, and let me highlight how the proof goes. It's really the same kind of proof as before, so you use this Shaw complement formula. Again, you can see that the terms out of the diagonal will be neglectable, but this time this guy will be large, and so this means somehow you pick at random a few of these terms, And so it stays random. So you cannot expect to get a quadratic equation as before. And what you can do, however, is, for instance, compute the Fourier transform of this guy to show that you have convergence in law of this variable. And when you apply the hypothesis, so here you can say, because these are independent, that you have the product of the Fourier transform of this guy, and they are all going to be approximated by this function of these parameters. And so you can see that this is approximately 1 plus the expectation of this guy. Okay, and then you can see that the Fourier transform or this kind of parameters satisfy a closed equation by using the assumption that I had just here, okay, which was just in purpose of the proof. You can see that if you plug in again a Schur complement formula on this hypothesis, then you get something which again depends on the Fourier transform, and so you get a closed equation for the Fourier transform, and you can prove that this equation is going to converge under the unique solution, showing that your Fourier transform converges. Okay, and then if the Fourier transform of this guy converges, so this means the convergence in on this guy, and so this means that your Stieltjes transform will also be given by the resultant of this variable which converges in law. So it will also converge in law, but the description of the limit will be much more involved. Okay, and in fact, so what I want to highlight here is that what we can see that in these Eviter matrices, the empirical measure of the eigenvalues is not really the natural quantity because it does not satisfy closed equation. It's more this type of more involved quantity which are going to be natural. So this means that you take the resultant on the diagonal, but you sum a function of them. You don't sum these guys, which would amount to take the trace, maybe in the previous framework where you have a Stieltjes transform, you sum more complicated function of the matrix, and this will turn out to be very natural things to do when you have Eviter matrices, and this will be the motivation for the introduction of this traffic distribution that Camille Male introduced, and I will show you what this is later on. So is there any question about these two results and proofs? Oh. Okay, but so what I want...
So the measure sigma phi is still deterministic?
Yes. So you can actually, because somehow you have to think that this guy, they will converge to some variables which are independent and with the same distribution. So when you take the renormalized sum, here you can use the law of large number, and the limit will be deterministic, but the idea that yes, the resolvent and the diagonal is going to be still random. Yeah.
And do you know if phi is nice, if the measure has like a density or?
That's a very good question. So that's actually so it depends on phi. So if phi is identity, clearly we have the semicircle law, we are good. So if for Levy matrices, we have lots of nice property. Actually, we know its density is analytic, except in finitely many points. Actually, we believe it's everywhere analytic. And this was key, actually, to show that you have universality of the local fluctuations. So this was some work of Schramm and myself, and then of Tiao and Agarwal and Lopato, showing that if alpha is greater than 1, you have you have a nice you are still in the universality class of the Gaussian matrices, so you have the same type of airy processes as the one you see for the GOE. But what is interesting is that if alpha is smaller than 1, then you have kind of a transition in the local fluctuations. So this is still quite mysterious. But for this guy, for instance, so if you take only a equal to 1, so you know that there is infinitely many atoms. Okay, for the Adair-Shruni graph, there is a very nice paper by Justin Salez showing that you have atoms at every real algebraic number. So these are roots of polynomial with integer coefficients. Okay, and if you take the Hadamard product with A, I believe it's the same. Okay. So basically, in this, I don't know. So this is kind of related, but yeah. So here you have no atoms. Here you have atoms if you have B, and if you have A, I would guess that most of the time you should have also atoms. But I'm not. Yeah.
If you are invited without setting the note and you at alpha equals 2, do you still get the sinusoidal law?
No. So this is what I'm saying. So this limit depends on phi.
Yes, that's very. But if alpha equals 2, is it also?
It converges towards the semicircle. Yeah. Okay. Yeah. So if alpha goes to 2, yeah, I think we showed that. Yes. Yeah. So actually, on part of the big open problems about Evitel is understanding the local fluctuation in this type of cases because of all these atoms, but there is also an absolutely continuous part. This was shown by Bordenave, Virag, and I forgot someone else. So there is an absolutely continuous part, but a dense set of atoms, so it's quite difficult to analyze local fluctuations. Any other questions? Because after that, I will go to the non-commutative setup. So where you look at more than one matrix. No, not yet. Yes. I wanted to show you another proof of this result about Evitels, which is completely different. And it was followed, for instance, by Bordenave, Caputo, and Shafai. And it used a marked graph. And this will be important in the rest of the talk. So what is the story of marked graph? So if you think about this matrix, which is this Hadamard product, you can kind of think about it as the adjacency matrix of a marked graph. So what is a marked graph? So you can think of B as the adjacency matrix of R-Schrödinger graph. Okay, so you put an edge with Big is equal to 1. And the marked graph, you will just put on each of the edge the mark, which is Aij. Okay. So on here, I will assume it's symmetric. And then, so you can think as this marked graph as a rooted graph. So you can choose a root, and then you put on the marked graph the Benjamini and Schramm topology. So what is that? So the idea is that if you have a graph, okay, so you look at some, so maybe you have chosen your root to be here, and you look at another marked graph. So what you will do is you will say that they are closed if you can find a bond of size R, so that there is an isomorphism psi from one to the other, so that it will match the edges and the marks will be closed, delta closed. Okay. So now what this topology means is that up to isomorphism, your graphs are very close, one from the other. Okay, so this allows to define a distance. And what they showed is that the marked graph, Gn, it will converge towards the Galton-Watson tree with marks, with low mu and degree distribution Poisson of parameter p. So what is that? The idea is that you draw so the limit is a tree, okay, and you can draw, for instance, at the root the edges with probability which is following the Poisson p. The degree will be taken according to that. And then you continue to draw the other edges with the law of the Poisson p conditioned to have already one edge. And so this allows you to draw the Galton-Watson tree with Poisson p. And then you just put marks which are IID with low mu on that. Okay, and what does it mean that the marked graph converges towards this limit? It means that this object, which is called the neighborhood distribution, is going to converge weakly. Okay, so when I first looked at it already, it was a bit, gave me some headache. so what do? You choose a root at random, and you take the sum of this direct mass of this rooted graph. So what does it mean? It means it's a weak topology. So you're going to test that against function on rooted graphs, which are continuous for the Benjamini and Schramm topology. And this will say that this converges over the integral under your limit object. Okay, so that's what this means. And so, okay, that's very nice, but what about the empirical measure of the eigenvalues? So the point is that the empirical measure of the eigenvalues is a continuous function of this negative distribution. So if you could show that this guy converge, also the empirical measure of the eigenvalue will converge. And so let's see, where is this? And so how can you see that this is a continuous function? In fact, it's kind of a contraction. If everything goes well and your matrix is bounded, it's enough for you to consider this type of object. Okay, you want to show the convergence of this object towards some finite moment. And if you think about this, this is a sum I of xi, I1, x ik minus 1, I. Okay, and this is I1, ik minus 1. Okay, and this is just a function of your map graph with a root I. Okay, because you are just looking, so if you think this will be 0 when you don't have an edge, and otherwise it's just a walk of length k, going from the origin, from the root to the root. Okay, so you see that somehow if you are allowed to take moments, your empirical measure, the moments of the empirical measure are just specific functions of the neighborhood distribution, and from this it's clear that you have this statement. Okay, so it's really now the idea that we will follow later on is that actually Evitier matrices, very differently from light-tail matrices, you can really map them to graphs which will be locally finite, and that the right topology to put on this graph will be the Benjamini and Schramm topology, and this will give us in turn the convergence of the empirical measure or the non-commutative law of several matrices.
So for the moment, this is an alternative proof?
Yeah. Yeah. This is an alternative proof, but the point is that it generalizes quite easily, much more easily than maybe, well, I mean, for non-commutative stuff, it's much easier to see it in terms of these marked graphs, and also for large deviations. Okay. Okay, I have to, well, maybe I will not go to the end, but okay, so what do we want to consider now? We want to consider these several matrices and take polynomial in several matrices. That's what eventually the type of problem you can come across, to have to deal with the asymptotics of the trace of polynomial in several matrices. And so the right space for the limits of such object is what we call a non-commutative law. So it's a linear form on polynomials, which is positive, which has mass 1 on threshold condition. Okay, and okay, so one of the nice results that Voiculescu proved is that so if you take matrices which are, let's say, diagonal matrices, and you assume that the empirical measure of the eigenvalues converge of these matrices, and then you conjugate them by R unitary matrices, then you can assert that the trace of polynomial in these matrices will converge. Okay? And the limit can be described by what is known as the law of M free variables with these distributions. Okay, and the definition of freeness is given here, but I mean, it's not important for the second. It just tells you that if you take mixed moments of your matrices, it will vanish provided that each of the marginal are centered. Okay? So the problem when you deal with heavy-tailed matrices is that they have no reason to look at all like approximately are unitary invariant. So unless actually, so for instance, this type of result would be exactly true if you would take matrices with Gaussian entries. They would satisfy that they are invariant in law if you conjugate them by unitaries. If you have only matrices with light tails, you could see that approximately they would be actually invariant in the sense that the limit would be the same. Okay? But if you have heavy-tailed matrices, don't look at all like this because these unitary matrices have lots of tiny entries and your heavy-tailed matrices are very sparse, so they are very different. Okay, so to deal with that, Camille Male introduces traffic distribution. Okay, so let's look at it with some patience. So somehow the idea is that you are going to take a more complicated function of the entries of your matrices. Okay, so your test function, they will not be polynomial, but they will be graphs, connected graphs. And what you would say that to each of these test graphs, which are your test function, you associate a number. It's just going to be a product of the entries following an edge, and you multiply the entries according to these edges that are in your graph. So this graph can be colored, so this means that you put here a matrix number LE if you have n matrices. And it can be, well, here it's indicated they are not self-adjoint, you can also take Y or its conjugate. Okay, and then you take the sum over 5, which are every map from the set of vertices to 1n. Okay, so it's kind of a generalization of the non-commutative law because so it's actually the same type of proof. So if you take H, so to be a cycle, okay, then what you will find is that so maybe you have the matrix L1, L2, L3, and so on till Lk. Okay, so then what you can see that the traffic of this specific graph is just going to be 1 over n, the trace of xL1, xL2, xLk. Okay. So somehow what the traffic is doing is asking to evaluate more function of the entries of your matrices. And this is somehow in relation with the fact that I was telling you that if you want to study the law of these heavy-tailed matrices, looking only at trace of resolvent is not enough. You have to go in a bigger space.
Why is this called traffic?
What?
Why is this called traffic?
So I think Camille said that when he studied that, some people told him, oh, it's like traffic in some algebra. And so he called it traffic, but at the end I think that the term is not completely clear. But he called it, that's the point. He created that and called it traffic distribution, and then it bears the name. But yeah, there is nothing to do with cars and stuff. Not that I know, at least. Okay, so that's the definition. And so the nice thing about traffic is that, okay, first you can show that it converges. So it's a bit like, so if you take only one matrix, you have nice assumption like this Adama product. And here I assume that you have convergence of the moment, but it's very similar to the assumption I made before. For instance, so if you have this Adama product times entries A, you can see that you have this convergence. Then you can see that the traffic is going to converge to some limiting traffic distribution. So this means that for all graphs, you will have convergence of this traffic distribution. And so what is very nice now is that now if you have, let's say, two matrices, and you would like to take the traffic of two matrices, if you know the convergence of the traffic of each, and you know that the law of the matrix is invariant by permutation now, then you have convergence of the traffic of both. Okay, so it's a bit generalization of the theorem of Voiculescu. Before you had like two matrices, you were assuming unitarily invariance, and then you were getting limit to the free distribution for the trace of all polynomials in the two. Here, if you have convergence of the traffic, so you assume more, but then you get the convergence of the traffic of the joint matrices for free towards the free product. I will not define what this is, but it's a well-defined object. And of course, so all the Evitern matrices I showed you, their distribution is invariant if you act under permutation, because we assume that the law are IID. Okay, so if you exchange row and columns, you're not going to change the distribution. So this assumption is very weak, much weaker than utilitarian invariance. Okay, so that's a way to get limiting traffic. Okay, any question about that? No? Okay, and so the first thing that we realized in the work with Charles and Camille, that actually this notion of traffic is very close to the notion of neighborhood distribution for a marked graph, where now the marks have colors depending on the matrices. So this means that if you have n matrices, you will have edges of color I, which is in between 1 to n. And so if you have this BIKL, so in this case, which is 1. And then what we realize is that this neighborhood distribution, the map which associates to the neighborhood distribution, the traffic distribution, so as I showed you, if you can take moments, it's kind of contraction, so this map is continuous, and actually it's injective, and the inverse is continuous. So somehow what we realized is that this, I mean, it was not a big realization, but we realized that somehow the notion of traffic, or the notion of this marked graph equipped with the Benjamini and Schramm distribution, is kind of the same data. Okay, and this will be important for the less than 10 minutes of the talk. Okay. And so now I come to the non-commutative entropy. So were there any questions about traffics? But okay, so somehow the big advantage is that you require more data, but you get more at the end of the day. Okay, so non-commutative entropy. So I mean, I go back to the talks yesterday about Voiculescu entropy. So what was the Voiculescu entropy? What is Voiculescu entropy? So the idea that you take M of this Gaussian matrices. So now you have light tail matrices, and even the entries are Gaussian. Let's say complex, so they're from the GUE. And then you ask, what is the probability that the non-commutative law, it doesn't go to this free product, but it goes to some other possible non-commutative law. Okay, so it's large deviation. So what is the probability that you see something unexpected there? Okay. And so if you want to define this more precisely, so what you would like is that when you take any kind of monomials in your matrices, it will be close to the limit. Okay, so you take all monomials, let's say, of degree less than k. So here it should be a distance epsilon. So the problem with always is that the topology of polynomial is not good if you have unbounded variables. So you bound your variables. Okay, and so this is nice topology now. And you take the probability of this, you take the log, so you have to divide by 1 over n squared, and you take the lim sup as n goes to infinity. And so once this is done, you will take the limit with epsilon going to 0, and you take the limit when k, the degree, and r are going to infinity. Okay, so that's the notion of, and this is similar to Shannon entropy, which is counting, for instance, if you are given a series of 0 and 1, what is the probability that you see NP once in this series? It's going to be given by the relative entropy. That's kind of the definition of entropy from a microstate point of view. Okay, so the problem with this entropy is that it's not yet clear whether you can replace the lim sub by a lim inf, and this is an important issue. So there is only an upper bound, and the lower bound is really complicated, in particular because we don't even really understand when this set is going to be empty, which amounts to this Kahn's question: when are you sure that given a mu you will have a sequence of matrices so that this converges to mu? Okay, so
Star is something that has an explicit expression.
yes, I mean it's explicit. It's kind of explicit. It's given in terms of Fisher. I mean, you can use actually. Well, it's explicit, but not easy to compute, I would say. Okay, but anyway, so this entropy was still useful for its application to von Neumann algebras. And what we also know about this entropy is the case where you have only one matrix. And then you have an explicit, so you can replace your full aggregation principle. You can replace the lim sub by a lim inf, and you have an explicit formula for the entropy. And this, in this case, it's very easy to derive because somehow So now the question is the probability that. So yeah, recall something that I didn't maybe point out, that when you have only one matrix, the non-commutative law is just the empirical measure of the eigenvalues. So if you look at the probability that this is close to a given profile, so in the case of GUE, you have an explicit distribution, okay, which is given by this Bordenave determinant. Okay, and so that's a normalization constant. So you have what is called this Bordenave, this explicit formula for the eigenvalue. So of course it's very nice. And what you can realize is that approximately this is like minus n squared times this entropy as defined here that you take in at ln. So this is only approximately. Okay, but so the density, if you put this in the log, and you forget that you don't have the diagonal term, somehow this is approximately this guy. And so if chi was continuous, well, you would just say I can replace the empirical measure by the mu, and under the product measure, this is a probability of order exponential minus n, so I will get that this probability is of order exponential minus n squared times chi of mu. Okay, so that's a pretty easy result. And so this is this entropy, which I asked yesterday could be related with the entropy that came in the talk of Professor Suzuki. Yes. Okay, so that's what we have. And now, what did we do? We wanted to do the same thing for evitered matrices. And so this is kind of what we succeeded to do, but so we have to condition our matrices to be kind of bounded as before, because otherwise the topology of traffic is not good. And now the speed is not 1 over n squared, but 1 over n, because you have this eviter kind of effect. And what we could get in this case is the full large deviation principle. So if we look at the probability that the traffics are close to a limiting traffic, then we can replace the lim sub by a lim inf, and we have kind of explicit formula for that, but which is too nasty that I decided not to show it to you. I can say some words under torture. Okay, and then what is also nice is that because we have this lim inf and lim sub, we have a nice entropy which satisfies this servability type of, which is kind of the reason why we would like for the Voiculescu entropy to prove that the lim sub is equal to the lim inf, that once we have this, it's quite obvious to get this type of properties. Okay, maybe a last result, which is that we were also interested in the case of one matrix. This was also unknown. And what we could do was to get large deviation for the empirical measure of the eigenvalues in this case, which is just a probability measure on R. So the speed is also n. And we get the rate function. So this could be seen in this case to be a consequence of the previous result. And we have a moderate proof, and this is the usual weak topology. And this also extends to Levy matrices. Okay, so in this case, we can also see that the rate function is minimum at sigma phi that I showed you before.
So the distance is measured in terms of...
So here it's classical distance. You can take the Wasserstein distance. So now it's just the empirical measure of the eigenvalue. So it's the quantity measure on the real line. And here this is a distance like Wasserstein distance. So this is kind of the alter ego of Voiculescu entropy for one matrix with this thing. So the rate is not n squared, it's n, and the rate function depends on the model. And again, it's even for one matrix, its formula are not so bad, but are not very easy. Okay, and the idea of the proof in one slide, because I'm going toward the end of my talk, is to come back to this neighborhood distribution of the Mach graph. So we have this Mach graph. We know that the traffic distribution or the empirical measure are going to be smooth function of this neighborhood distribution. So it's enough, to get the probability that this, to get large deviation for this neighborhood distribution, okay, because size of balls are similar. And then there was a very, very nice paper by Charles Bordenave and Pietro Caputo, where they could prove the large deviation principle for the neighborhood distribution of the Erdős-Rényi graph. So this means when you have only x equal to b. Okay. And so they could prove that by really showing that it's a counting problem. You are asking, you have this edge given at random, and you try to figure out what is the probability that this neighborhood distribution has a given limit. And it's to do that they introduce this generalized configuration model, and they could count the number of configurations which gives this type of large deviation event. Okay, so that's a case where y is only b, and then you can extend, the point is that you can extend this proof to the case where you have Machs, so provided they are discrete, because then it's again a problem of counting configurations. And then you can eventually approximate continuous maps by discrete Machs and show that somehow your large deviation will extend by approximation. So that's what we call exponential approximation. So that's kind of the approach that we have. Yes. Okay, so I think I am done. And so what I wanted to show you in this talk is this kind of so you have these big objects, and so you have these big random matrices, and also now this big random graph. And somehow I think that there was kind of this nice Benjamini and Schramm convergence arriving, which is a kind of nice relation for heavy-tailed random matrices. So large deviation can then be derived for mark graph by this combinatorics when you have this discrete graph, these discrete marks. And yes, what I didn't say is that the rate function is finite only at random locally finite mark-rooted trees, so which gives you some property a priori on the entropy, which are on the traffics which are finite entropy. And also, so what I said is that you can extend this kind of approach to Levy matrices, again by approximation, because if you truncate your heavy-tailed entries by being greater than some threshold, then you are really in this framework of Hadamard product. So you have to go to Levy matrices, you need to do another approximation, so you don't use only mark graph, but what we call networks, which are limits of mark graph. Okay, so thank you very much for your attention.